Hello everyone. So the topic of my work is 1D description of the constant 2D system of electrons in rotating harmonic trap and the generalization of the system. So the work is done with my guide Gautam Mandal, Ajay Mohan, my colleague, and myself Rushikesh Suroshe. So let me start with the system we are in our consideration. So consider there are n electrons in the 2D plane which are going which having the small omega as the some harmonic oscillator potential, and the system is whole system is rotating with the angular velocity capital omega. So this is the Hamiltonian for that system. From here we can calculate the eigenfunctions, and from there we can calculate the energy eigenspectrum. So this is the system we are in our consideration. Now we can make the following type of canonical transformation from x1 x2 p1, from xy px py to x1 x2 p1 p2. In this new coordinate system, the Hamiltonian is given like this, where you can see the eigenfunction has the similar structure like the eigenfunctions of the harmonic oscillator. Now come to our problem. So we force the following two constraints on this side, on xy px py 4D space, which is m omega x equal to py and px equal to minus m omega. Under this constraint, these constraints are reflected as x1 equal to 0 and p1 equal to 0 in x1 x2 p1 p2 coordinate. So the constraint Hamiltonian is given like equation 9, but the interesting is the classical Dirac bracket of xy becomes 1 upon m omega, which gives us hint that y acts like canonical conjugate to x. So hence, we may say that the 1D harmonic oscillator system in x2 is effective system for a constant 2D system. But we are demanding something more. We want what exact quantum mechanical 1D 2D correspondence between these two properties. So our claim is we find that the exact correspondence between Wigner function and the probability density as given like this. So we are comparing here the 2D quantity rho xy with the 1D quantity ux2b2. And equation 11 we get that the rho xy, the 2D quantity equal to ux2 p2, the 1D quantity in the small h cut limit and the large n limit. We showed this in the graph, they're matching. Once again extend their horizon and ask the question what will happen to the dynamical states. In the dynamical state also we get some same type of results as given in equation 12, but there are some nice properties about the Wigner function for n particles slightly determined state, which are that u square equal to u, which means that u can be 0 or 1, and this gives the entire configuration of phase space of fermion is described by Fermi droplet, which is shown in the graph. And del tu, which means the time dependent of Wigner function, we can calculate from this Poisson bracket. And here we can say that there is no time dependent, it is symmetric in time. Mhm. But there is another approach to solve this puzzle, and we claim that in the rho xy follows the if the rho xy follows following this property, then we can claim that uxp equal to rho xp. In the last 1 minute, I want to go to the my generalized problem, and then I'm adding this gamma upon r square terms. We are exactly the same dependence, but our constant Hamiltonian is not very easy. So hence, our goal is to find some clever way to find this x1 x2 p1 p2, which will simplify this constant Hamiltonian. But however, in the classical limit, we are able to show that u theta p theta equal to rho r theta. And the underlying result for this equality was density of the probability density peaks at r square equal to lambda, which double implies that the angular momentum should be equal to L. And this exact result we got from the Wigner phase space density. To proceed with approach 2, we use this approximation, and this approximation we find that our probability density should satisfy this equation, and then we our next goal is to match this profile between the eigenvalue density and with the Wigner function. Thank you very much.